Hello everyone and welcome to the Stepcraft live series. Today we're going to talk everything and anything end mills. We're coming to you from the apocalypse of 2023, or what it feels like out there. Our entire northwest corner up here in Connecticut and the tri-state area is covered in smog coming from Canada. So hope everyone out here is doing okay, breathing all right, and our friends up in Canada, hope you guys aren't burning too much.
It looks really weird outside. They're having their wildfires and literally it's like you're stuck in a cloud. You could barely see across the street, and it smells like you're at a campground outside. That's all.
There's an orange glow, so
yeah,
I was pretty sure there might be some zombies that interrupt us during this, but hopefully we'll be okay.
We'll see what happens.
So today we're going to talk about one of our most requested topics, and that's end mills. End mills can be the easiest thing, and they can be the hardest thing that you can deal with because there's just so many different options. So we're going to start with what an end mill is and what it isn't. So generally speaking, when we say an end mill, a lot of people think router bits, a lot of people think drill bits. That drill bits and end mills are two different things. And the difference between a drill bit and an end mill is where they actually cut. You can see we have a little graphic here showing the cutting area of an end mill. End mills are designed to cut from the side. They're side loaded, they do everything with the side cutting, whereas a drill bit, the cutting area is directly above that tip there. So everything is done right in this little cone here. That's why when using an end mill, when CNCing with an end mill, the hardest cut that you're going to make is that initial plunge cut. With most woods, maple, hardwoods, it doesn't really matter. It's not going to make much of a difference. But when you start to get into harder materials like aluminum, that initial cut, that plunge rate is going to be very important because the end mill is not designed to cut with the tip here. So a lot of programs like Fusion 360 will allow you to come in from the side where that's most efficient to cut. Vectric will not do that, but as long as your plunge rate is okay, you don't have to worry too much about it.
What you can do with Vectric though is you can set a ramp angle, so it will let you ramp into the material. So like on this particular end mill here, you can see that the cutting edge is from basically this corner up. So rather than plunging straight down in the material and then cutting laterally, what you can do is you can actually look your Z lower as your X and Y are moving, so you're kind of coming into the material at an
Think of an escalator.
Yeah, you're coming in like an escalator, right? And that makes the engagement point more directed to this corner of the end mill. One of the things too is a lot of people say, well, why is the end mill and the drill different? They both have flutes on them. Well, the flutes on a drill bit are not there to cut anything. They're there to simply take the chips that you're cutting from the tip and to evacuate them from the hole. Whereas on an end mill, the flutes are the actual cutting edge. So let's see what else we got here. I didn't mean to cut you off. You were in the middle of
yeah, so
talking,
that is generally, when you talk end mills, you're going to be talking the CNC world. Drill bits can be used on a CNC machine, but the RPMs are pretty low, generally speaking, when you're using that. So in the world, and when you're at Home Depot and Lowe's, when you're looking at end mills, that's what we're going to be using for CNC routing.
Correct.
So with that comes an entire library of different end mills that you can be using. So what we're going to do today, I think, is start with the basics of a general end mill, and then go into a few specialized end mills, an upcut, a downcut, and a compression bit. Explain the different uses for different materials from there. In a second episode, or a third even, I think we'll go more into the V-bits, more into surfacing bits, and get a little bit deeper in there. But here we're going to start with the basics.
Right. So right now we've got, one of the things we should talk about to begin with is the parts of an end mill. I want to make sure that everybody understands what the terminology is when we're talking about it. So we put together a mini course a while ago, and this is some of the excerpts from that mini course where we talk about the different end mills. So here's an example of the four basic parts of an end mill. So you have your overall length, which is from the end of the shank to the tip of the end mill. Your flute length, which is that's an important one because that's going to determine how deep you can cut with that end mill, how deep you can effectively cut with that end mill. So for instance, if this end mill had a 1/2 inch flute length on it, but you had to make a 1 inch pocket, you could still use this same end mill, but the shaft of this end mill right in here will end up rubbing against the kerf as you're removing material. So it's not ideal. It could be done in a pinch, but I would always try to get an end mill that has a flute length that matches the job that you're working on. So if you need to cut 3/4 of an inch, try to find an end mill that has a flute length of 3/4 of an inch or greater. Sometimes that's not possible. If you're cutting a 2-inch piece of a material, you may not be able to find an end mill that has a 2-inch flute length, but more importantly, you may not have the Z-axis height in your machine to support a 2-inch flute length, plus the stick out of the actual shank, plus your collet nut and your spindles. So you just have to kind of work within the parameters of what you have.
Yeah, and that's perfectly fine as long as your pass depth is not lower than that flute length. If you're doing a pass depth that's an inch and your flute length is only 1/2 inch, there's not going to be any cutting on that top half of that. It's just going to be rubbing there.
Correct.
So you're going to get your, and there's not a lot of situations where you would go that deep with a pass depth, but something like foam, for instance, where you're not worried about a deep pass depth, you have to make sure that's at least that much.
Right.
Otherwise, it's not cutting anything.
The cut diameter is self-explanatory. That's how big. Essentially, there's a term called kerf. And if you were doing a profile cut, or meaning you were just making one line in a piece of material with this end mill, that kerf is the width of the material that's being removed. And that will always match the cutter diameter. It's common in metal machining where that cutting diameter may vary. You'll see it shrink over time because it wears, and then you'll have features in your software to compensate for that. In a router, it's not really that common, especially when you're cutting softer materials like woods and plastics, that you really won't see that overall diameter shrink too much on that. So for the most part, a 1/4 inch end mill is essentially going to be a 1/4 inch cut diameter all the time. And then the last thing is the shank diameter. Shank diameter is interesting because we get asked that a lot, like what shank should I get for my machine? Now, I always recommend that you run with the largest diameter shank you can for your spindle. So if your maximum collet size in your spindle is 1/4 inch, try to run a 1/4 inch shank no matter what the final diameter of the cutting tool is. If you have a 1/2 inch capability, try to run a 1/2 inch. And what'll happen is, let's just say you've got a 1/4 inch shank, but you want to cut with an 1/8 inch diameter cutter. The shank will be a 1/4 inch, then it'll taper down to an 1/8 inch. And the reason you want to do that is the larger the shank diameter, the more rigid the end mill is. The more rigid the end mill is, the better finished cut you get, typically. Now, one thing you got to be careful of when you're using anything that tapers from a large shank to a small cutter is you've got to really pay attention to your pass steps, because your flute height or your cutting height on that end mill is critical, because you can't go any deeper since the shank tapers larger. So if you're using an 1/8 inch tapered end mill, you're going to make an 1/8 inch kerf, and if you try to go deeper than that cut height, your shank is not going to fit in that 1/8 inch channel, and you're going to end up with a problem.
Ask us how we know that.
Yeah,
It's happened a few times where we've left the machine running, we've come back, and there's a little bit of smoldering going on.
well, that, or you end up with a rubbing. You
Yep.
turn that taper into not really a round over, but almost like a chamfer bit, and you're kind of forcing the material in. So
And with no cutting edges, it's not cutting that. It's literally just forcing that down.
Right.
And you're going to get either, you could start a fire, at very worst, or it could just bend that edge a little bit. You're not getting a nice clean edge there. So your total shank or your cutting length should be at least that when dealing with a tapered.
Now, another thing to keep in mind is, another common question is, how many flutes should the cutter have that we have? That's more of a topic that I want to cover in this video. Just keep in mind a couple of things. The more flutes that you have, the faster the feed rate has to be. So the faster you have to run that end mill through the material, or the lower the RPM you have to run it. One thing has to give. Either you're going to have to run it, if say you're running at 15,000 RPM, you're going to have to run that end mill with 3 flutes much faster, your feed rate, than you would if it was a 2 flute end mill. Or you could run it at the same feed rate, but you're going to have to reduce your RPM, because ideally, and we'll talk about this in a minute, you want to maintain a specific chip load. So in our world, the most common flutes that we're going to use in a CNC router world are 2-flute and single flute. Those are going to be the two most common end mills that you're going to use in terms of numbers of flutes. Sometimes you might run a 3-flute. The advantage of a multi-flute or more than one flute end mill is you're going to get a better bottom finish. So if you were pocketing something out, you're going to get a better finish on the bottom than you would with a single flute end mill. But if you're just doing profile cutting and stuff, then I would usually lean towards a 1- or 2-flute end mill, and you can maintain the optimal settings for that particular CNC router machine.
In this episode, we're going to stay away from the more advanced cutters like foam cutters, diamond cutters for carbon fiber, because those are a little bit more of a specialized fluting system. We're just going to talk about the basic single and 2 flutes here.
Right. So this next slide, we've got some different cutters here that we're going to talk about. So we got an upcut, which if you look at an upcut, you can see that we're spinning the end mill clockwise. And if you look at the flutes on the end mill right in here, the spiral is going upward. So if this is spinning clockwise, it's taking the material, cutting it, and then moving the chips upward. A downcut end mill is just the opposite. So it's still spinning clockwise, but the flutes go in the opposite direction. So as this is spinning, it's shearing off the top, and it's forcing the chips downward. Now, there's one here that I'm just going to briefly mention, and only because it was on this slide and I didn't feel like editing it out, a straight cut end mill. A straight cut end mill it doesn't have any flutes. So it cuts evenly from the top to the bottom. So it cuts the entire cut of whatever it is you're doing is going to be sliced evenly throughout the entire process. The downside of a straight cut end mill is you're not evacuating chips. It's just they usually don't have really much spiral in there. So there are some cases where a straight cut end mill is kind of, almost like a universal tool, right? It'll do most things okay. It's kind of like a Swiss Army tool, I guess. You'll be able to find straight cut end mills pretty commonly at like Lowe's or Home Depot. So if you really were in a pinch and you needed a 1/4 inch end mill, you're probably not going to find an up or down at your typical big box store, but you most likely will find a straight cut end mill, and that'll get the job done.
And I think that's a really good point that you make, because you can get a lot of stuff done with a variety of different end mills, but the more you start to specialize and get into specific end mills for specific materials, the better results you're going to get. The more quality you're going to get, the faster you're going to be able to do it. So it's a lot of information at first, but don't let it scare you, because you can get a lot done with the basics.
Right.
But once you can start to specialize in this, you're going to see the results are going to just skyrocket.
Now the last end mill in the list is the compression, and in my world that's probably one I use the most. Now what a compression end mill is it's a combination of an up and a down cut. So if you look at the tip of the end mill here, you can see that it is actually an upcut end mill on the tip. But then in this section of the end mill right here, there's a transition where it becomes a downcut spiral. And where a compression end mill comes in handy is when you're cutting like laminates, like plywood, melamine, anything with formica on it, any kind of laminated material. Because as you're cutting through, you're pulling the bottom, when you cut through the material, you're pulling the chips from the bottom upward, so you're going to get a nice clean bottom cut, and you're pushing or slicing the material downward from the top, and you're going to get a nice top cut on it. So what you end up doing, though, it's called a compression, because it's essentially pulling the chips upward from the bottom of the material and downward from the top of the material, and it's compressing the chips in the center of the kerf, or in the center of your cut area that you're doing. And it's just, if you're going to cut plywood, the only way you're going to be super happy and 100% of the time be successful is using a compression end mill.
Yeah, so, there's really no comparison.
Right.
Once we started using compression end mills, it was night and day, the results. Now, the one downside of that is it does scream. It is very loud. It is very, very high pitched in there.
Sometimes it depends on the material that you're running. You will get, and it depends on your feeds and speeds. So you can get a little, it could be a little louder, especially with a 1/8" shank compression end mills tend to, they tend to make a little bit more whiny noise than say a 1/4 inch.
And if you're not used to that, that might throw you off a little bit.
Right.
But once you use it a couple times, you'll notice it's perfectly fine. The finish is still clean. It's quickly become one of our most used end mills.
Now, one of the things with the compression end mill is where there's a lot of uses for it that I have. Sometimes I'm running a job on a vacuum table, and vacuum hold down is better the larger the pieces you're working on. So the smaller the surface area of the part that you're cutting, the less vacuum force you have on it. So say you were doing a cabinet and you're doing the sides of a cabinet, which are pretty large, no problem. Your vacuum table is going to hold that down without any problem. But then let's just say to use up the plywood, you want to make the stringer that you mount the cabinet to the wall with, which is usually 3 or 4 inches wide, and it could be a longer piece. Well, that doesn't have as much surface area, so when you cut all the way through that piece, you have the possibility that you might lose vacuum. You might not have enough vacuum hold down force. When you use a compression end mill, because it's pulling chips up and pushing chips down, as you're cutting through, the chips being forced in that kerf keep the piece that you're cutting in the spot. It's kind of like think of it like a clamp, a side loading clamp. And so that's another advantage to using a compression end mill. I don't use compression end mills for everything, but definitely for laminates, so your plywoods. They do work really well for MDF as well. If you were running material like softwood, like pine or poplar, compression end mill is nice because an upcut, when you're running an upcut end mill, you're cutting the material and you're pulling the chips upward. And so on plywood, if you were doing it with an upcut, you'd end up with splintered edges along the top. It just wouldn't be pretty. Pine and poplar tend to be a little bit stringy as well. So depending on your feeds and speeds that you're running at, you're going to notice that your cut is not going to be as clean with an upcut end mill. Now, if you're cutting hardwoods like mahogany or maple or anything like that, your upcut should be fine for that application. And you get the added benefit with an upcut of you're making the cut and you're pulling the chips out of the kerf and getting them out of the way. You will notice that a upcut end mill will make more of a mess in your work area. So if you're not using dust collection, you'll get more of a mess with upcut because you are pulling the chips up and then shooting them out away from the end mill. Where compression is forcing all your chips into the material or into that kerf, you tend to have the least amount of dust and debris when you're using a compression end mill. A downcut end mill, we didn't really talk about, we briefed over it. So you might say, well, if your cut quality with an upcut on most wood is not, you don't get razor sharp edges, then why not just use a downcut on everything? Now, a downcut end mill is good for pocketing, for rabbets and dados, anything where you're not going all the way through the material, I would use a downcut. You're shearing the top, so you're always going to have a nice clean edge, especially in plywood. You're forcing your chips downward. The downside of a downcut end mill is when your bottom surface finish is not going to be as smooth. So if you were doing a cabinet where you're running a dado and you're simply going to glue a shelf into that dado, then you don't really care what the finish looks like. It's not something that's a final result. You're just going to put glue in there, and if anything, if the finish is rough, the glue is going to bite it more and you're going to have a better fit. But if you were doing something like I don't know, like a...
Something with a surface finish.
Yeah, like a charcuterie board that has a recessed pocket or something like that, then that bottom finish is important because depending on the size and shape of the geometry of your bottom finish, it may be very difficult to get in there with a sander to sand it out. So you want to look at using an end mill that's going to give you a better bottom finish for that. Now, if you're going to do a charcuterie board or something, you're probably going to be using hardwood, so an upcut is going to be more than fine for that. A compression end mill is the same thing. You're probably going to have a better bottom finish with a compression end mill, but you're not going to use a compression end mill mainly for pocketing. All right. So I know we said a lot of stuff, but in summary, an upcut end mill is going to be used for hardwoods for anything that you need to remove the chips and evacuate them away from your material. Now I'm talking about wood right now. A downcut end mill is going to be used for pocketing, rabbets, dados, pockets that you don't really care about a really smooth, beautiful surface finish on the bottom floor of that pocket. A compression end mill is going to be used for cutting all the way through laminate materials like plywood, or it's, like I said, good for MDF. So your compression end mill is going to be used mainly for those materials. And it's going to be used for jobs where you are cutting all the way through. You would not typically use a compression end mill for pocketing. It's just not something that that's recommended, especially because one thing that we didn't talk about with a compression end mill is the most important thing when you're running a compression, especially if you're cutting through plywood, is the distance between the transition from the tip from where it's an upcut to where it transitions to a downcut. That distance needs to be your first pass depth. So in other words, let's just say that distance is 1/4 inch. Then your first pass depth when you're cutting into your material needs to be a minimum of 1/4 inch deep, because you want to make sure that you're engaging the downcut part of that end mill on the top surface of your material. If you don't do that, let's just say you made your first cut 1/8 of an inch deep, then essentially it's no different than cutting your plywood with an upcut end mill, because that's the only flute that's available. There's absolutely no difference between the two. And you will end up with splinters even though you're running a compression end mill. We can show you in Vetric in a minute on how to set that, and I'll also show you on a Monotools website where you can find that information out. Okay, so that's another important thing. Now, another thing about upcut end mills, when you're cutting materials that are harder, like plastic or aluminum or brass or other non-ferrous metals, an upcut is typically the only way to go. It's a hard material. You want to get the chips out of there. With aluminum, you do not want to recut chips, so you don't want the chips to fall back into the kerf as you're going around for each successive pass step. So you want to make sure that you're ejecting those chips away from the finished cut, and an upcut end mill is what you're going to use for that.
Yeah, that's a great point, because what we've been talking about mostly up till this point is for woods, plywood, softwood, hardwood, but when it comes to plastic and metal, it is a different story.
Yep.
It is much, much more important to use the correct bit. You don't ever really want to use a downcut in a plastic or an aluminum.
The only time I would run a downcut on plastic is if I'm cutting some really thin plastic, let's say 1/8 inch or thinner, and I'm using a vacuum table to hold it down. I might use, in that case, because the material's not thick enough that the chips are going to cause me any problem, and it's most likely only going to be one pass. So if I'm only going through a 1/16 inch piece of plastic, my pass depth is going to be a 1/16 of an inch. One pass I'm cutting all the way through. In that case, though, because the material's so thin, using a downcut end mill is going to put downward pressure on the material, whereas if you were using an upcut, it's going to tend to try to pull the material up from the vacuum table.
We've been cutting material dye bond, which is a thin painted layer of aluminum with plastic underneath.
Correct.
And we had that exact issue where we were using an upcut, which we normally use with plastics, because it clears the material, it gets those chips out of there so it doesn't reheat. But the problem was it was gripping the bottom of the material and pulling it up with the vacuum table.
Yeah, especially if you're doing, like if you're cutting something large out of dye bond, it's not going to be an issue. But if you're using dye bond to make, like, say, 3-inch letters, you're cutting letters out for a sign or something, you don't have enough surface area on those letters for vacuum to do much a good job. So I would tend to gravitate towards a downcut. And in fact, on dye bond, my tool of choice for dye bond is always a straight cut end mill. That's one case where I do like a straight cut, because it's cutting through plastic and metal at the same time. It's cutting everything evenly. There's no upward or downward force, and it just works well for me. That's my tool of choice. But if I didn't have that, I would go with a downcut there to put some downward force on that material. So that's an advantage of an upcut end mill when you're looking at materials like plastics and aluminum. Now the thing with with plastics, what's important is you want to get those chips out of the way. Especially if say you're cutting through a half-inch piece of PVC or something like that, you want the chips to get out of there, because if you're doing multiple passes and you're forcing the chips in that curve, every time you run around, you're recutting those chips. You're causing heat. The heat is going to melt the plastic, and then it's going to kind of rebond itself behind the end mill. You'll really notice it when you're cutting acrylic. If you're cutting like plexiglass or acrylic, if you don't have your speeds and feeds set just right, where you're ejecting chips away, you're going to see that you're essentially welding the chips back together as the end mill moves through the material.
Probably happens to almost everyone who cuts PVC, plastic for the first time, or even aluminum. If you don't do that right, if you don't evacuate those chips, it re-welds to the cutter, and then your cutter's toast.
Right.
That's it. Especially with aluminum, there's really not much you can do at that point. Plastic, you may be able to get it off, but it happened to us the very first time we cut plastic, and we weren't in there. We're recutting those chips, reheating them, and we got chip weld. So chip evacuation is the most important thing with plastic and aluminum specifically.
Now, another thing that, we had mentioned a few times, I mentioned speeds and feeds. So I want to get into that here, and we're happy to answer questions both online and offline that you might have. And we're also happy to revisit this. So if somebody were to say, could you spend more time on speeds and feeds or spend more time on applications, we can certainly address that in another live. It's just Greg and I were talking before this recording tonight, and I wanted to cover up, down, and compression end mills because those are the most universally used. Greg was thinking about maybe we should talk about ball nose, V-carve, surfacing, and all the other types of bits, just because those are the basic categories. So we had two different ways of looking at this, and so we definitely agreed that we're going to do another part 2 or part 3 even of this end mill series, where we talk about 3D carving and what end mills do you need to use in speeds and feeds, and we'll also talk about V carving and using V bits, and then we'll talk about surfacing and other form tool bits and things like that.
This may be one of those videos you may have to pause or go back and look at a couple times, because we're trying to pack a lot of information into a short amount of time.
Yeah, we're trying not to make this a 2-hour video.
We could spend a couple episodes, we could spend 10 episodes just talking about end mills, feeds and speeds, and the theory behind it. The good news is the basic stuff that we kind of go over here, you can get a very, very long way. Now, like I said before, the more you specialize, the better results you kind of get. But if you can kind of get the basics down and get a few good feeds and speeds, calculators, charts there, you're going to go a heck of a lot further than you were when you're just starting.
Right. All right, so let's dive into some feeds and speed stuff. So we are an Amana partner here. 90% of all our tools in our demo center are all Amana, probably more than that. Love the company, love the tools, high quality tools. Pricing is really good, but moreover, they just have a cutting tool for every application. So their website is really good. There's a lot of information here to help guide people when they're looking for something. So we've been partnered with them for years. We love it, and that's what you're going to hear us talk about on this. So if you're a fan of Whiteside or other tools like that, I'm not saying anything negative against any other tool. It's just these are what we have the most experience with, and we love them. So we're gonna build everything around that. Now here's an example page, the 46102K. This is a solid carbide tool bit. It's a 1/4 inch diameter and a 1/4 inch shank with a 3/4 inch cutting height, and this is an upcut end mill. So here's an example of a typical upcut. What's interesting here is this information. You want to pay attention to that, because what they're telling you here is that this is an upcut flute. It's a 1/4 inch diameter, so the cutting diameter is a 1/4 inch. The cutting height, the flute height, is 3/4 of an inch. So if I was going to cut 3/4 inch plywood and I wanted to cut all the way through, then this would be the end mill that I would use. Well, that's not true. If I was cutting plywood, I'd want to go with a compression, but what I'm saying is material thickness, this is what I would use. You're going to use a 1/4 inch, this has a 1/4 inch shank. The overall length's 2.5 inches, and it's a 2-flute end mill. So why the overall length is important is you've got to keep that in mind, because you always need to be conscious of your stick out. And the stick out is there's a picture here. This is your stick out. It's from the bottom of the collet to the tip of the end mill. That's how much stick out you have. And most of their end mills have a little line laser engraved on it, and that line is where you want to put the tool when you put it in your collet and tighten it down.
It is not gospel. It
It's
doesn't
not.
have to be. It's a very good point.
Right.
But if you find you're running on a Z height and you need to chuck it up a little bit higher, you always have that option as long as you don't cover up the flutes.
Right. I would, yes, you could definitely go higher. I would not have it stick out more, though.
And the reason for that is deflection.
Deflection and, your deflection. And
The more your tool sticks out, the more you're going to have a little bit of deflection in the tool, and the more deflection, the more chatter you're going to have, and nobody wants that.
Right.
So it's a good starting point. Don't go any lower, but you can always go higher if you need to.
So now they also give you an example of what materials you might use this end mill with. So this is, I'm thinking, representing solid wood. They are showing this with a plywood, but this, in my opinion, would probably be more like Baltic birch. Baltic birch is a higher grade of plywood with very little to no voids between the laminates. The laminates are really tight together, and an upcut, there's less chance an upcut end mill in Baltic birch would splinter on the top layer. But if you're using cabinet grade plywood, just typical stuff you would buy like at a big box store to make kitchen cabinets, that is not Baltic birch. There's less plies, and there's going to be more voids on the inner ones, and you definitely will see splintering on that. Now the other one that they're showing here is a laminate, like a melamine or with a formica bottom, but because this is an upcut end mill, notice that they got the laminate on the bottom. So they're talking about when you cut all the way through, you're slicing upward, so you're not going to affect that laminate that's glued on there. You're going to have a nice, clean, crisp edge around it. So this gives you kind of a visual as to what you would use this end mill for in terms of materials. Now, one of the most important things here is the speed and feed rate chart. If you click on that and then you click on download PDF, that'll open up on the screen here. And this is important. There's some really good information here. So what they're saying is that the CNC operating spindle speed is 18,000 RPM. So they're saying everything you see on this chart is based on that spindle running at 18,000 RPM. Your depth of cut is 1 times your tool diameter. So in the case of a 1/4 inch end mill, your pass depth is 1/4 inch. So every time you take a pass, you're removing a 1/4 inch of material. All right. So now, what was the? Oh boy, I forgot. What was the model on that end mill? That was a 46102.
46102.
Okay. So we're going to go back to this chart, and we're going to look up 46102 upcut. Tell me when you see it, because 46102. Okay, right here. Okay.
Wow, good eyes.
Yeah. So these are the numbers that we want to concentrate on. Now, they have different feed and speed settings for wood plywood and for MDF and laminate. Okay. There's a couple things that we want to look at in here. The feed rate in inches per minute is how fast you're going to set that end mill to cut through your material. The chip load per tooth is how much, let's just think of it like the size of the chip that's being removed every time a cutting flute takes a chunk of material away, for lack of a better term. That's the size of the chip that's being removed. And then they have a ramp down on this particular chart, which is usually 50% of the feed rate. So they want you to plunge a ramp into the material at half the speed that you're running and cutting through the material. Okay, so those are the 3 things. Now keep in mind, you're going to set your RPM at 18,000. Depth of cut is 1 times the tool diameter, so in this case it's a 1/4 inch. And what they're saying here is that we want to set our feed rate to 180 inches per minute. And when we do that, we should see a chip load of 5 thousandths. Okay? If we were to cut the MDF laminate, that is going to step up from 180 inches a minute to 215 inches per minute. And our chip load will be bumped up to 6 thousandths. Now, this is a standard recommendation. This is not, again, the Bible. This is where you would start. And even at that, it's not where you would start on every machine. Okay? So if you're running like a heavy duty industrial machine, whether it be like our Q series or any of the other heavy duty machines that are out there on the market, I would start with these book values on that end mill, hands down. If you're running a lighter duty machine, like a belt driven machine or something like that, you may want to run your depth of cut a quarter of that. So instead of a 1/4 inch, you may want to run it a 1/16 inch. It just depends on how durable your machine is. Now, for anybody that's a Stepcraft customer, what I usually recommend as a starting point, if you're running a D series machine, I would take that depth of cut and I would divide it in half. So in this case, I would run that end mill at 1/8 inch depth of cut per pass at 18,000 RPM. If you're running an M series machine, then I would take that number and I would go 3/4 of that number. So without a calculator, instead of a 1/4 inch, you'd probably be closer to 0.2 inches, somewhere in that range. So that's just purely based on the spindle power and rigidity of the machine in comparison to like an industrial grade machine. All right. So what I want to do is I'm going to switch over to Vectric for a second because I want to show you an example of what we're talking about here. So we're going to go in. I'm just going to go ahead and select a tool. Let's select a 1/4 inch end mill. This doesn't necessarily have to be the Amana tool, but what?
It's very important to note too, I get this question almost daily, is we have a generic setup of tool library in here right now. So all the tools that you see, generally speaking, we may have 1 or 2 on the left here, but these are the generic tools that come with VCarve, with Vectric. These are not necessarily a good place to start. These are kind of placeholders in there for most of them. They don't take into account your machine, your material, anything. They're just kind of there. So a lot of customers will try these and have very, very mixed results. It may be close, it may not be.
Right.
So the first place you should always start is with the tool that you are, the dealer that you're working with. So in our case, we're going to go to the Amana website. We're going to get all the information right from that tool page, the diameter, the pass depth. We're going to go to the feed and speed chart and start there based off the series you have. That's going to give you much better results than trying to use these values. These values don't take into account anything that you're doing. So if you're getting kind of bad results right now and you're using just what's in there, that's exactly why.
We should probably do maybe in a live, we'll take some time and we'll go over the tool library and Vectric, or the tool database, because this is important. They have different materials, different machines. You could have one end mill that you use on multiple materials, but it may have a different feed and speed rate for each material. So you could have that one end mill in the library, but based on the material that you select, it would vary. So
Yep.
I don't want to get too far into that here because that we could talk an hour just on that.
Amana does have a database that you can download and load into there. So there are some advantages to that to get you a little bit closer.
Right. So if this was me and I was going to run that end mill, I would go ahead and probably change the name on this end mill, and I would copy the name from the Amana site, put it in there, and then I go and I set the settings. So it's a 1/4 inch end mill diameter, but it is a 2-flute end mill, so we're going to change that to 2 flutes. Our pass depth we've got set at a 1/4 inch because that's what the speed and feed chart is. Let's just assume that we're doing this on a Q series, on something that's more rigid. Step over is used when pocketing. That's how much of material you're going to remove widthwise per pass before you make another pass. Think of it like mowing the lawn. You're going to go in one direction, you're going to slightly overlap as you come back so that you don't have a strip of grass that you didn't cut.
So the lower the step over, the less
finer
it's
the
going to
finish.
take. You're going to get a great finish, but it's going to take a while because you may only be taking 2% more material each pass.
Right.
The higher the step over, the finish may not be as great, but it's going to take way less time. If you're doing a 90% step over, you're taking 90% more material each pass.
Right.
So there's a balance there, and we can probably spend a whole episode talking about that as well.
But here's the thing, I always use 40. I never go higher than 40 on that. So if I'm pocketing, I never go more than 40%. If I'm doing something that requires a very nice bottom finish, I will lower that number. I'll usually go down to 15 or 20%. Yes, it's going to take longer because you've got to do more passes for a given distance linearly, but that's what I would do. So just if you take anything from this podcast or this live, keep that at 40. as your max, and then your min could be 15 or 20 depending on the finish you're doing.
And your 3D carvers out there might want to go a little bit less than that, get a little bit more detail.
Yeah, it's
but
possible.
That's for a different day.
So speeds and feeds, again, that chart was, everything was at 18,000 RPM, and the feed rate that it said was 180.
Let's toggle
So
back
type that in,
there.
180. I can't reach the key. And then we're going to do a plunge rate of half that, which is 90. Now, you can see right here, automatically Vectric calculated a 5,000 chip load on that. So we're going to go back to this chart, and 46, 102, where were we? Quarter inch, down here. So we were, as you can see, at 180 inches per minute, we're at 5,000s. So that calculator is working correctly on the Vectric website. And then if we up it to 215, then we'll see that it should go up to 6 thousandths of a chip load. All right, so if we go back to Vectric and we change this now, because now we're going to do the MDF. So if we make this 215, you'll see that chip load goes to 6 thousandths. Now, why is this important? That chip load is the optimal range that manufacturer is specifying for that tool to remove, for a chip to run in its optimal efficiency. It's going to give it the best lifespan. It's going to give you the best finish cut on your projects. So we have a lot of people that have some very, without knowing, some people are like super cautious. Like, as an example, if I'm running this job and I'm like, wow, 215 inches per minute, that's a lot. I'm new to this. I don't want to push my machine too fast. I don't want to, I want to take it really easy. That's something we hear every now and then. So now we're going to say, well, you know what, I'm not comfortable going any more than 40 inches per minute. So type 40 in there. Now you can see that my chip load is 11 10,000ths, or less than, or it's just a little over 1,000th of an inch. Now, if that range for that end mill was 5 to 6 thousandths, I'm running literally 5 times less of a chip load on this end mill. Now, what's going to happen is I'm going to shorten the lifespan of this end mill because I'm not removing enough material to take full advantage of the cutting flute on that end mill. But I'm also not going to get a chip. I'm more likely going to see dust when I'm cutting. So instead of getting nice chips, I'm going to see a pile of dust like an anthill. The other thing I'm doing is I'm rubbing. When you don't take enough chip out away from the material, your end mill, your cutting flute on that end mill is rubbing along the edge of the material. And that rubbing creates friction. Friction creates heat. Heat will destroy a carbide end mill. So while you think you're doing the machine and everything a favor by running it slower, you're actually not. You're lowering the lifespan of that particular cutting tool. Now, the other thing that you're doing is you're running the RPMs excessively high on the spindle, and you don't need any of that power because you're not removing enough chip, okay? So in this case, think of it like driving a car around in first gear all the time. Like, there's other gears to take some of the stress off the engine and to take that power and divide it out. When you're on the highway, you could be in 5th gear. You don't need to be in 1st gear. So it's the same thing here. So what we can do is if we, for some reason, if we want to stay at 40 inches per minute, we can play with the RPM to try to get that chip load back up into that 5,000 range that we want. So if we go to 10,000 RPM on this, you see now we're at 2,000 of a chip load. So we're still less than half of what we need to be. And unfortunately, on most router spindles, you're not going to get an efficient power or speed down below 8,000 RPM. So if we put 8,000 in there, the best we can get out of this end mill is 2.5 thousandths on that, which again is still way below where it needs to be. But we could bump the feed rate up now to 80, and now we're going to be at 5,000 chip load. So if I want to run that at 8,000 RPM for some reason, I can bring my feed rate down to 80, and I'm still getting that same 5,000 chip load, which is where I want to be. So the take of this is just keep in mind on that feed and speed chart, that chip load is your target. That's the number you're always trying to hit when you're running a job. And you're going to adjust either your feed rate or your RPM to get that number to where it needs to be. In a case where let's just say your machine can't go 170 inches per minute.
That's a great point.
Maybe you have a small desktop machine, it maxes out at 120 inches per minute. Let's just say that, for example, because 120, like our M series machine is, no, that's millimeters per second.
Millimeters per second.
Yeah, so let's just say on your machine, if the most you can do is 120 inches per minute, you'll see that if I run 8,000 RPM at 120 inches per minute, I'm at 7.5 thousandths, which is over. It's too much. Now what's going to happen there is I'm going to cause my end mill to deflect. I'm going to put excess strain on the machine and the spindle because I'm trying to take a larger chip than the end mill is actually designed for. So again, I want to hit that target of 5,000. So we're going to go to the RPM now, and we're going to readjust it. So let's try maybe 12,000, and that should get us closer. Yep, 12, how about that, right off the bat? 12,000 RPM put us exactly at 5,000. So if I want to run this recipe of 120 for my feed rate, and I run at 12,000 RPM, I'm still hitting the optimal chip load. So I'm going to get the most life, the best cut, and everything based on that. So I'm hoping this makes a little bit of sense. It is a complicated topic, but if you just simplify it by looking at, I'm always trying to target that chip load. Now, the other thing to keep in mind is, again, like I said before, depending on how rigid your machine is, you may not want to keep the pass depth at 1 times the tool diameter. But changing this, so if I change this to an 1/8 of an inch or a 1/16 of an inch, it doesn't have any impact on the chip load. The chip load, because my RPM, that's determined by my RPM and my feed rate. So the only thing that's doing is putting excess strain on your machine by trying to take a deeper pass than your machine is physically capable of doing with that size end mill. You're not doing yourself or your machine any favors. So there's a few things there, and like I said, I think if you stick with that rule of thumb, that on a weaker machine, like a belt-driven machine, I would probably go on a 1/16 of an inch pass depth on this tool, maybe 1/4 of the recommended. On our D series, 50%. On an M series, 75%. And then on a Q or any industrial machine, just take it for the face value of whatever the speed and
Now, that's a
features.
very generalized statement. That doesn't take into account material, anything like that. So consider that a good starting point, but that's not like we talk about gospel.
Correct.
That can be adjusted. If you're cutting foam, it's a whole different story. But generally speaking, with most materials, that's a good starting point.
And that's important too, because a lot of people ask that, like, where should I start? And the nice thing is, like with programs like machine control software, especially like our UCCNC, there is a feed override and an RPM override on the screen. So if you start at this recommended settings and you're running your job and it sounds good, almost like the machine's hardly doing anything, you can increase your feed rate and listen to it. Your machine, your ears are going to be a really good gauge as to how well everything is set up. Okay, so if your machine, when you're running at these settings, sounds like it's squealing, it's making all kinds of noise, it's chattering, then by all means, lower your feed rate, drop that feed rate down, and see if it goes away. The other thing you can do is raise your spindle speed up and see if it goes away. All right, so you have the ability to play with it. No two machines are identically the same, so I would focus on what it sounds like and staying on book value for those settings. Very complicated topic. There's a lot, and this is one of the reasons why Greg and I were talking before it started, why I didn't want to get into any other end mills besides these 3, because there's feeds and speeds, there's applications, materials, it's crazy.
And this is almost the perfect topic to kind of bring to our live series, because you can interact with us. You can let us know, hey, I'm trying to run, a certain material and I'm having some trouble. Let us know your feeds, your speeds. Maybe we can do quick Q&A.
Yeah.
Get some answers out there, because we have a lot of experience with all different sorts of materials, and we know the machines, inside and out. So
Yep.
that's we haven't really gone
Yeah.
to the chat yet.
So we have a couple of questions here. What is the maximum RPM you can run for a given router bit? So again, the maximum RPM is usually going to be determined by the manufacturer's speed and feed chart. If they don't tell you an RPM, but they do tell you a chip load, again, you're going to play with your feed rate and your RPMs, and you're going to try to get that optimal chip load. Your RPMs could also be set by your spindle. For instance, like on our Q machine, we run an 18,000 RPM spindle. So if you're running an end mill that has a max RPM of 25,000, it doesn't matter. You're gonna set your feed and speeds to 18,000, and you're gonna adjust your feed rate because you can't go any faster than that. So I come from a different school of thought on this. I don't like running anything with an engine, anything with a motor. I don't like running anything at its max if I don't have to. So if I have to run my spindle at 18,000 RPM, then I want to make sure that I'm setting my feed rate to get my chip load in that range where I'm utilizing 100% of the efficiency or the power of that spindle. What you don't want to do is run at 18,000 RPM and then run a very, very low chip load where you're hardly taking any material away, because now you're running that spindle at full speed for no reason. You're cutting the lifespan of your spindle, the bearings, the brushes, whatever, and it's unnecessary. So that's why most spindles have a speed control. Not everything needs to be run at 100 all the time. Sometimes you'll get a better cut quality, a better finished product by running at 12,000 RPM. So, just don't be one of those people that you put the spindle in and just crank that speed to max all the time. And I only do that if you're planning on making other adjustments in your program to put enough load on that end mill so that that spindle is being run efficiently.
Now, with that said, 18,000 is a very common RPM range, so don't be afraid to set it there, but not if you don't have to.
Right.
You'll probably find a lot of stuff you're doing is in the 16, 18, 14 range-ish. We work quite a bit there.
Yeah, exactly.
But if it doesn't have to be, don't be afraid to put that down.
Right.
Put it down to 12, 13, 14, and see how it does.
Now, along those lines, another question we got was, what is the leading cause of dulling? What causes an end mill to dull out or not last as long as it should? And the biggest culprit of that is heat. Carbide end mills do not like to get overheated. Now, keep in mind, one thing that we had this discussion with a customer yesterday, I think. A lot of people don't realize this, but when you remove a chip, after you take a cut, every time a chip evacuates from that end mill, it's extracting a little bit of heat from that end mill. Now, we're not talking about a huge amount, but it's a little bit. But when you think about how fast that end mill's spinning, and if it has more than one cutting flute, that's a lot of chips flying away. And it is taking heat from the end mill that would then transfer to the spindle itself, and it's removing it. And especially when you're cutting metals, it's huge. Like when you're cutting aluminum, each one of those chips is a little mini heat sink, and it's pulling heat away from that end mill. So when you're running a job and you don't get that chip load where it should be, and you're running significantly lower chip load, where in this example we use where you'd have a 5,000th is recommended, but you're running at 1,000. You're rubbing. You're not removing chips. You're rubbing. So you're not creating any chips to remove heat. You're creating excessive rubbing on there. That's going to turn your end mills black.
Yep.
And
Turn into more heat.
As soon as the end mills turn black, forget it. It's done. It becomes dull at that point, and then it's going to smell and smoke and do all kinds of other things. So the number one cause of short lifespan on end mills is heat. And the easiest way to keep the heat down is to adjust your feed rate and your RPM to stay in the optimal chip load zone for that end mill. So let's see, when should I use single 2 flute or 3 flute? Okay, we did talk about that briefly earlier. For plastic and aluminum on a CNC router, I always go single flute. I just do. They're harder materials. I want to get the chips out of there. A good example of that is, let's switch over to here. So here is a Amana 51407, which is a O-flute end mill that is designed specifically for plastic. So you can see it's got a single cutting flute on it. One other thing they have is they have these ribs along the cutting edge, which are kind of cool. And what those are is only the tops of those ridges are making contact with the sidewall of your material as you're cutting. So instead of you cutting a chip and then this entire vertical wall is rubbing against the plastic, only the tips of these ridges are there. And it helps with cooling. It helps keep the cut cool. It helps your finish. They call it a mirror finish, and it just, you get a much more polished finish on the edge when you're cutting with these tools. And you got a quick chip evacuation because it's only a single flute, and the helix or the spiral diameter or shape on this is pretty large. So on plastics and aluminum, I always, this is what I suggest. I mean, here's an aluminum end mill. This also is an O-flute. They call it an O-flute, but it's a single flute. They use the same kind of mirror finished edge on there when you're cutting your aluminum. Again, very nice wall finishes when you're done. But you quickly are going to get that chip and get it out of there. The other thing is, keeping in mind, if you go to 2-flute, you have to make some adjustments in your feeds and speeds. So most routers are going to run well within their operating range using a single flute end mill. Okay. If you're running wood is 1 or 2 flute is usually fine. 2 flute if I'm doing pocketing, and it's important for me to have a good bottom finish on the pocket, I would run a 2 flute. I may even run a 3 flute if I can get the feeds and speeds so that the RPMs are low enough. But I would run a 2 over a 1 if I'm looking for a good bottom finish. And again, to go to a 3 flute, you're going to have the best finish quality, but you're going to have to make some adjustments on your feeds and speeds that may be outside your machines and your spindle's capability. Okay, so
Now, a little bit of an easier answer to that. I think we've kind of browsed over this, but what's really awesome about the Amana Tool website is if you just truly have no idea where to begin, they will start you with, per material. What are you looking to cut? Whether it's aluminum, plastic, wood, and they'll recommend bits per the material. So you can kind of get an idea of what you're looking at. You'll notice a lot of single flutes are in the plastic categories, the aluminum categories, and that I think is best for more starters because you can kind of learn based off just how they categorize things.
Right.
You can find the different specialized bits. If you pick a material and go from there, Amana Tools does a really good job of separating all that. And if you've ever been to our facility here, we have an Amana tool box that basically separates each bit into a category, whether it be aluminum, wood, and you'll find the compression bits are in the categories there. And that's probably your best place to start if you're just completely new to all this. If everything we're saying here is completely over your head, that's a good place to start.
another good place to start is calling Amana or a company like Tools Today online.
Or give us a call.
Give
We're
us
always
a call.
here to help as well.
There's always, even shoot us an email. Hey, I'm thinking about running, oak, and I need to use a 1/4-inch end mill. What do you recommend for my speeds and feeds on my Stepcraft M1000? And we'll tell you right away, here's exactly what I would start with, and that would be a good place for you to go. So you always have help available. You're not stuck on your own when you're getting into this, because there's certainly a lot of information here to absorb. A couple other questions. Why would I use a compression bit over a straight bit when cutting double-sided melamine? So if you have a piece of melamine essentially is like an MDF with like a Formica on both sides, used commonly in cabinet work and stuff like that. Because the compression bit is designed to compress the material, and it will avoid chipping. So you have that upcut. When you're cutting through the material on the bottom, that upcut tip is pulling the chips upward, giving you a nice clean cut. And at the top of the material, you have a downcut, where a straight bit could potentially work, but depending on the quality of the melamine, because you don't have a spiral in the flute, you run the risk of having chipping and things like that happen. So compression is definitely going to be the way to go. Let's see, we have another question here. Customers sent a support, Roger, he sent a support video of a noise the machine's making. Curious if my 1/8 inch end mill was set in correctly. I removed the ATC head from the spindle just now and it's free spinning. I'm not.
Yeah, Roger, give me a call. We'll get online. We'll talk about that and see if something is going. It's very possible it was set incorrectly, and we'll be able to see that right off the bat.
Now, one thing that we did run into at another customer call yesterday, that their spindle was getting excessively hot, and in that particular case, after looking at the feeds and speeds, I'm pretty confident that it was a situation where you're running outside much lower chip load than what would have been required for that end mill. So I think that particular customer was running at full RPM without having any real load on that end mill, and that's what was starting with overheating. So if you are in a situation, no matter what machine you have, and your spindle's overheating, where it feels warmer than it should, I would start by looking at your feeds and speeds. Make sure that you're not rubbing, that you are taking a load on that end mill, and that you are doing a pass depth, because rubbing can also be on the tip of the end mill. It's not just always on the side. So for instance, if your end mill should be a 1/4 inch pass depth and you're only taking a 1/64 of an inch, you may be rubbing along the bottom of the end mill too, and that's just as bad for it. So another thing to keep in mind.
Jordan, our friend from Ireland. Hey, Jordan, what time is it there in Ireland? It must be pretty late.
Yeah, it's late.
Yeah, I appreciate you joining us, though. But Jordan asked, can you sharpen end mills? Yes. Yeah, most end mills you can. There are companies who do that. I would say it probably depends on the company.
Yeah, I don't know how to do it myself, to be honest with you. I don't have the time to learn. So I would just take them when they get dull and I send them out and have them done. But there are companies that will professionally
definitely
sharpen end
possible.
mills. Especially when you're spending a lot of money on an end mill. It's nice to know that you can keep using it for a long time in the future. Yeah, that's actually pretty good for questions, I think.
Yeah, I think we are just over about an hour here.
About an
so
hour,
I think
which
this
is where
is
you want to be. This is a
good time to wrap it up. I know that was a lot of information. Part 2, we're going to continue, maybe part 3, 4 even. Let us know if this is helping you guys. Send us any feeds and speeds questions you may have. We're always here to help. We're always here to learn new materials and the advantages. We know your machines inside and out. So let us know. Let us know if this is helpful, and we will take it next week.
Yeah. Again, we appreciate you joining us, and we really enjoy doing these things. As you can tell, between the two of us, we have an awful lot of information to share, and we want to keep doing them, so your feedback is very important to us. But until the next one, thank you again for joining, and we will talk to you very soon.
Stay safe.